Before looking at the problem of model order selections, let's first look at the problem of linear one-step ahead prediction. So a linear one-step ahead predictor is a circuit which takes a stochastic process x of n, using time-delayed samples of that process weighted together in some way, tries to estimate the next sample of that stochastic process. So the general problem faced in linear one-step ahead prediction is to find these coefficients so that we can get a good estimate, and good here being in the minimum mean squared error sense, or the mean squared error sense. Now, it may not be intuitively clear what this problem has to do with spectral estimation, which is the topic of this lecture. However, one can see that depending on the spectral properties of this process x of n, we may or may not be able to predict it ahead of time. So for instance, if x of n is a white noise process, meaning that the samples are uncorrelated in time, then clearly knowing past samples will tell us nothing about future samples, and we wouldn't be able to do a very good job of predicting a future value of this process. On the other hand, if x of n was a highly predictable process, like a sinus process, then knowing past of that sinus process would allow us to study its behavior and very accurately predict where it's going in the next sample. So conversely, our ability to predict the process ahead of time will tell us something about the spectral properties of that process. So beginning with a question, so if we assume that x of n is indeed a sinus process, meaning that x of n is given by an amplitude times sinus 2 times normalized frequency times the time variable plus a random phase. So we'll assume here that the phase and possibly the amplitude are both random, but the frequency of the sinus process is deterministic. Then, what would be the smallest number of values we need of x of n to be able to compute the next value? So that meaning if we have past samples, we have capital M past samples of this process, how many such past samples do we need in order to compute the current or the next value of x of n? So would we need 1 sample, 2 samples, 4 samples, or would we in fact need an infinite past of this process in order to be able to accurately predict the future of the process? Well, the correct answer to this question is option number 2. So we will in fact only need 2 past samples of the process in order to predict the future value. So we can see that by assuming that we have this sinus process with unknown amplitude and phase, but with a known frequency. So taking this expression that we have here and using simple trigonometric rules, we can rewrite it in the following form, such that we can identify a past sample of x of n, so namely 1 step past, and another sample of x of n 2 steps into the past. And the coefficients in front of these terms involving x of n would be the optimal weights to choose in a linear predictor of a future value. So what this implies is that a future value x of n plus 1 can be computed from x of n and x of n minus 1, or equivalently the value of x of n could be computed from the value of x of n minus 1 and the value of x of n minus 2 without explicitly knowing the unknown. So we see that these 2 weights don't have to be dependent on the unknown quantities, which is a and theta in this case. So in order to generally find the optimal weights for our 1 step ahead predictor, let's consider a slightly more general case of simply estimating a random variable y from a random vector of variables, or a vector of random variables x, in an MMSE optimal way. So we know that a linear detector has the following form, that we obtain our estimate by doing a weighted combination of the samples in this vector. So W here is simply the set of weights in the general linear minimum mean squared error estimator. So hopefully from previous courses you know that there is an explicit formula for computing the optimal set of weights for a linear detector, and has the following form, that it relates or it obtains the weights through a linear equation involving an autocorrelation matrix for this vector and a cross correlation vector with the thing we wish to estimate and the random vector which we know, or our data. And this can be written either as a linear system of equation or explicitly as the optimal weights is simply giving us the inverse of this autocorrelation autocorrelation matrix times this cross-correlation vector. We also have an expression for what the minimum mean squared error is given such an estimator, and it's simply the variance of the thing we're trying to estimate. So the variance that we would have if we didn't have any data to base our estimate on, minus an expression which looks like this, which can be viewed as the reduction in uncertainty that we have from knowing x of n. So the reduction in uncertainty provided by this linear detector. So this can be applied to our problem of one-step ahead prediction. If we assume that what we seek is x of n, namely that y is equal to x of n, and that what we know is the past samples, so x of n minus 1 up to x of n minus capital M. Then one can simplify the expressions for this autocorrelation matrix and the covariance vector in the following form. So the autocorrelation matrix would simply be based on the autocorrelation function of the original process x of n, which we have put in this vector, and this cross correlation can be worked out to be the following expression. So when one sees this, it should ring a bell. So this looks very similar to something that we've seen before. So essentially what it is the Yule-Walker equations. The only difference is that we've now called the vector of values w, and that we're missing a minus sign which appeared in the linear Yule-Walker equations for the AR model. So what we realize is that the optimal coefficients in a linear one-step ahead predictor are the same as the parameters of the ARM model that we use to fit to the data, apart from this sign difference. And moreover, we can look at the last parameter of the ARM model, namely the B parameter, or the constant gain. And we can write out that expression. So the expression we previously had was that B0 was given as the square root of this expression. So therefore B0 squared is simply given as this expression involving the ARM parameters and the autocorrelation. And this we can write more compactly using this cross-correlation vector and putting all the coefficients AM into a vector A. Meanwhile, for the linear one-step ahead predictor, we had this expression for what the minimum mean squared error was, and it looked like this, which we can rewrite using the fact that our optimal weights were given by the inverse covariance matrix times this cross-correlation matrix, which we simply plug back into this expression and obtain the following expression. So if we now compare these two expressions, we see that they are also quite similar. So for instance, we know that the power in the process y is equal to the autocorrelation, or the power of the stochastic variable y is equal to the autocorrelation of the process x at time lag 0, because putting in time lag 0 simply provides the power of the process. And also, since w is equal to minus a, we see that the second term is in fact also the same. So what this means is that the parameters that we estimate in an ARM model, so the B0 squared parameter, is equal to the minimum mean squared error that we could achieve with an optimal linear predictor. This actually provides a way for selecting the model order of ARM models. So while it's not immediately clear how the parameter B0 squared would depend on the ARM model order, it's quite clear that if we choose a longer time window in which we observe the process X, we will be able to predict it better into the future. At least we cannot do worse. And this means that the mean squared error would always be non-increasing in the model order and generally decreasing if we improve performance. But since the mean squared error of the MMSE predictor and is the same as this B0 squared parameter of the ARM model, we can also say that the B0 squared parameter of the ARM model must be decreasing in the model order M of the AR process. So what this means is that one may choose the model order in an estimation of a spectrum by increasing the model order until we see no further significant reduction in this B0 squared, at which case we can conclude that we've accurately modeled the underlying phenomena. There are a number of criteria based on this realization which tells how to choose the model order. So two of them are the Akaike information criteria and the minimum description length. And where this comes from, we will not go into any details, but it's interesting to look at the structure of these two criteria. So the Akaike information criteria says that we should choose the model order M such that it minimizes the following expression. So the following expression is the sum of two terms. The first one is the logarithm of B0 squared for that particular model order, and the second one is a term which relates the model order to the total number of data samples that we had n. So one can see that if we increase m, then this term will decrease, meaning that we in general get a better fit of the model. Meanwhile, what we saw is that even if we can get a better fit, not of actually of the model, but of the data samples that we observed, we're at the risk of over-parameterizing the problem and fitting too tightly to the observed data and not the underlying process. So it makes sense to penalize the solution for choosing the model order too large. So that's why we have this second term, which grows with m. So generally, what the Akaike information criteria tries to do is to strike a balance between how small we can make this B0 parameter and how large we have to choose the model order in order to do so. And the minimum description length criteria has a different form, but it includes the basic same reasoning. We want to make B0 squared as small as possible by choosing m large, but we don't want to choose m too large, and therefore we penalize solutions that give us a very large m. So let's consider a question related to this. So assume that we want to fit an AR model to our data and that we have at least 8 data samples to work with. And we consider these two model order selection criteria. So the Akaike information criteria given by the following expression and the minimum description length criteria given by this expression. So which one of these criteria will give us the smaller model order? So will the Akaike information criteria give us the smaller order? Will the minimum description length give us the smaller order? Or will they give the same order? Turns out that the correct answer is option number 2. So the minimum description length will give a smaller or at most equal model order to the Akaike information criteria. And the way to see this is to compare these two expressions. So if we normalize by n in the model or minimum description length, that doesn't actually change the criteria since the minimum would be attained for the same m. And then we would have m times logarithm of n divided by n, which can be compared to this term. And if we have more than 8 samples, logarithm of n divided by n will always be greater than 2 divided by n, meaning that the minimum description length will penalize large model orders more heavily than what the Akaike information criteria does. And therefore, the minimum description length criteria will give us the smaller model order of the two. So in order to interpret these results, let's again consider the problem of selecting the model order for our estimator for the AR4 process. So suppose that we choose a 0th order model to begin with. So a 0th order AR model is simply a model without any feedback. So it's simply the constant gain, and all we can hope to do is to estimate the power of the underlying process. So even if we have 256 samples, this is the best estimate we can come up with, simply a line saying matching the power of the underlying process, but we cannot actually match the shape of the process. If we move to an AR1 process, we can have a slightly shifted shape, but we cannot create any peaks in the spectrum, and the best estimate would be given by this line. So at an AR model, we are seriously under-parameterizing the problem, and we cannot come close to the true spectrum with this estimator. So increasing the spectrum to an AR2 parametric spectrum estimation, and this one we've seen before, we can create one peak, but since the true underlying spectrum has 2 peaks, we cannot really match that. We can move to a model order 3, which still allows us only to create 2 essential peaks, and we still cannot match the spectrum. But then when we move to an AR4 model, which matches the model used to create the data in the first place, we see that we suddenly get a very good estimate. So increasing the model order beyond this, for instance to an AR5 model or an AR6 model, doesn't significantly improve upon the performance of our spectrum estimator. And again, if we move to high order, we can match the actual data samples that we obtained in these 256 samples, but we will not match the true underlying process because we've just over-parameterized seriously the problem. So we can now look at this B0 squared parameter that we have in our AR model in order to see if this tells the same story that the spectrum estimators just told. So if you plot the B0 squared for a specific model order m as a function of that model order, we get the following curve. So what we can see is what we observed, that for a model order of 0, then the B0 squared is simply going to be the same as the power of the process. But as we slowly increase the model order, the fit to the original spectrum gradually becomes better, which we see as a reduction in this B0 squared parameter. And we see that we get some reduction for even a model order of 1. Then we have a switch to 2, but we didn't see a great improvement when we moved to model order of 3. But then, as soon as we moved to model order of 4, which is when we matched the underlying process that was used to generate the data, we saw again a dramatic improvement, and this is where we hit both of those spectral peaks. But moving the model order much above that does not in general improve performance. So we see a very, very slight increase in performance, or actually fit to the data, simply because the data is a realization and not the true stochastic process itself. But given 256 sample, which is the basis for this plot, we see that past model order of 4, there is really no significant improvement in terms of this B0 squared parameter, which means that we are justified in choosing the model order of 4, which in this case matches the underlying process. And this is what the Akaike and minimum description length criteria would give us in this case, because it would penalize us choosing higher orders by this penalization factor in the selection criteria. So simply looking at the forward gain of the AR model, we can determine what a good model order is for our spectrum estimator based on the AR models. So to summarize, there is a deep connection between AR modeling and one-step ahead linear predictions. And essentially, the one-step ahead linear predictors is equivalent to the AR model for the data that we observe. And this connection can be used to motivate and to select the AR model order in spectrum estimation. In general, we've seen that the model order should be chosen high enough so that we model the data, but it shouldn't be so high that we start modeling noise, or we actually fit the particular realization rather than the statistical properties of the spectrum or of the stochastic process whose spectrum we wish to estimate. And this is called overparameterization. It's something that we want to avoid, and we avoid this using these model order selection criteria that was shown previously.